Just yes. Right. So let us just see that. No, once again, my thing, everything just went away, right? So, but we have the idea. It is like this. And then you have to just take a term and just break it up. Okay. So this you write this as 2 minus 1. You write this as 3 minus, no, 3, wait. 1 minute. You would want to get a 3, right? So you write it as 3 minus 1. 1 minute. Yeah, no problem. This is right. And then you write it as 4 minus 1 times 3 factorial, and then maybe 5 minus 1 times 4 factorial, and so on. Right? Then if you open it up, you get 2 factorial minus 1 factorial. This was 2 factorial here. Right? You see, now is the thing. This 3 times 2 factorial is 3 factorial, and this part 1 times 2 factorial is just 2 factorial. And then 4 times 3 factorial is 4 factorial, but then this you get a minus 3 factorial, and so on. You see now the cancellations are taking place. That's what we want. You see, in this way, the things are getting canceled, right? This will get canceled with this. This 3 will get canceled with this. Nothing will get canceled with 1, and so that's why it remains. And like this, it will cancel with this. And you can see, you can go all the way. Try to write this out. Okay, it will be good. You will get 101 factorial minus 100 factorial. But the 100 factorial would get canceled with something previous, right? With the previous terms. Thing. And so you'll finally get this 101 minus 101 factorial, sorry, minus 1 factorial. Okay. This is what we have. I mean, this is not the most interesting way to do this question, but this is a technique that would work in many places. Okay, is everybody clear about the technique? Because this will be used in summations in different places. Okay. However, as I was saying about the combinatorial interpretation of what is going on, right? That would give a very enlightening proof in some sense, but I don't know if it's easy to come up with that. Okay. See, the point is that the right-hand side suggests something very combinatorial. Okay, this is a combinatorial number. What I mean to say is that it has very simple combinatorial meaning. This is like, I mean, this is like, so can anybody think of a question? Now this is, so usually the questions are there and we just find the answer. But from this expression, looking at this expression, okay. Now this is interesting because it's like an open-ended question. You can think of many different kinds of questions. Okay. So the question here is think of a natural problem. Okay. A natural, I don't mean in nature, but like the way it's stated, it shouldn't be like we're putting artificial conditions, but just think of a problem. Okay. Think of a problem. Okay. Just a counting question whose answer, and being able to do these things, you know, in a way that you can make this things work is really why combinatorics is useful outside combinatorics. Okay, outside in different other places. Okay, whose answer, and that really allows us to prove these things. Right now we're proving them for numbers, but then it allows us to lift these things to other places, because the numbers may go away but the reasoning remains. And then you start proving this thing for polynomials because the same reasoning you use there, and then you prove it for many different other kinds of things. Okay, because reasoning is more powerful than numbers. Like numbers are just one, you know, one set of things on which we do interesting things. One set on which we do interesting things. Okay, so that's why we are interested in ideas here. So think of a natural problem whose answer is the RHS. Just this, and then obviously you know what you can guess maybe what the next step should be. That, but this is only the question I'm asking to do. But then the next question would be then, can you solve that problem in a different way so that you get this LHS as the answer? Okay, and then you would know they're equal because you have solved the same problem in two different ways. Okay, but for the time being, just think of a natural problem whose answer is the RHS. Yeah, please say yes. Yes, yes, no problem, no problem. Okay, yeah. Yeah, so that is, but that is just a change in notation, right? That's right. So this is certainly right, but this is just a notation. Yeah, but in fact, you see, writing these things in the summation form right now, it seems like making things more complicated. But in some time, you will see that writing it in the summation form can actually facilitate manipulations. Okay, can make it, can actually suggest manipulations also. Okay, because then you see it through algebra, the expression as an algebraic expression and so on. But right now, it is too simple to really write it like this. It just makes it more complicated, in fact, maybe. Okay, but later on, we will replace this k by a k square, maybe by a polynomial in k and so on. So then maybe it will become interesting. Okay, but right now it doesn't seem to help us. But what is a combinatorial question? What is some combinatorial question that you can think of for which the answer is RHS? Okay. Think of this for homework because this is a testing question, and then try to see if you can do this. This is not simple. If you can do this, is very nice. So it's a high risk question. If you can get it, it's very nice. Otherwise you may just be stuck. Okay, but just try it out. We'll discuss this the next time. Yes. Now let us just move along the lines of algebra. If maybe you can just note it down also, though it will be there in the video, but you can just note it down, it will be easier. Uh, yeah, so if you just keep that. And yeah. So the next question that I want to ask is just similar, but just algebraically more complicated. Okay. And that is like this. So, yeah, maybe we can just write it, but for the time being, let's just 1 minute. So that's 2 times 1 factorial, 5 times 2 factorial, 10 times 3 factorial, and you guys can already see the pattern, 4 factorial, and so on. And so on, I'll just say till 50 terms. I'm not writing the 50th term. You have to figure it out or do something. Yeah. Now we want to see if we can add this again in an interesting way. Let's see. So maybe this is the problem number 2 in this. Kind of, yeah, that's basically in the end what it is. And then we would like if we could simplify this further and get a very crisp answer that we don't know yet if it's even exists. Okay, something which is like this, or just a few factorials. So first of all, let's try to understand what should be the 50th term. That is the thing. No, according to this pattern, according to this pattern. So this is a very different, I mean, this is numerically, these two are very different questions. Conceptually, they are similar, we'll see same ideas. In this, what should be the 50th? Because I mean, unless we know that, then if we can't figure this out, then we don't even see a pattern at all. But then it will be difficult. That's why we should try to figure out the 50th term or figure out the pattern here. What is the pattern? Even in these terms, what is the pattern? Okay. Yes, anyone? In the terms themselves. Yeah. Okay. That is that is a rather complicated way to say it. 50 square plus 1. Y minus 1. Something like that, right? Yeah, it should be 50 square plus 1, right? Because this is 1 square plus 1. Yeah. That's right. Right. But Pragya, what you said is also correct. It's in fact, it's a correct thing, but it's a bit more complicated than what we need. Yeah. See, yeah, so that's right. I mean, what 17 is 2 plus is 2 plus 3 plus 5 plus 7. No, wait a minute. That's not true. 5. Yeah, it's right. Yeah. And this is okay. So that maybe that way we can get another interpretation. I don't know if it help. But yes, so this 10 is 2 plus 3 plus 5 and so on. And so this is, so you also now have a formula for adding the first 50 odd numbers and in general first n odd numbers. So this is 2 plus 5 plus 3 plus so on till the 50th odd number. So the 50th, yeah, the 50. So here we have the 3 odd, the third odd number, starting from 2, not from 1. So yeah, and so like that you can do. So 50th odd number would be what? 2 into 49 plus 1, right? Something like that. Yeah. So it's 2 into 49 plus 1. So that is 99. Yeah. 99. This is also correct. And in fact, now we have a formula that if you add odd numbers from, if you add the first k odd numbers, then you get k square. Not a 1 because this one is extra 1 is coming because of this. That's a different formula which we have spotted here. You can try to prove it. Okay, but we don't need it right now, so we'll not write. So there are several interpretations, as you can understand. Okay, but now how do we do this? Now we understand the pattern. How do we do this? And now what Unav had mentioned previously, that can be useful here, just to view this like this. So the summation. So this just is a symbol for the following. It just says that this summation, it starts from k equal to 1. It ends at k equal to 50. Okay, and at each term, so the summation, which you can read it as a plus. Okay, at each term you are just taking that kth number, squaring it, adding a 1, and then multiplying k factorial. This is just a notation. Okay, it's not necessary, but it can help you to think about, okay, what to do. So you may or may not use it. It's not important. But essentially, the idea in the end is that we need to look at the kth term. You need to look at a particular term, and you need to be able to write it in a way that, maybe as a difference or something which can finally simplify the thing. Okay, the kth term. So we know that the kth term is this. How do we deal with this? So this problem is algebraically a little more involved, but we'll do it. Let's see. So just like the previous question, we have to start writing it using differences. Okay? You have to write this as difference of some things. How can we do that? So this each term we need to break it up into 2 parts or 3 parts, maybe, we don't know. Yes, go on. Sorry. Yes, please say, you were saying something. Okay. Yeah, yes, the idea, see, the idea would be, I don't know exactly what you're going to say, but we have to write this as a difference of things. That's what we have to do. How can we do it? That is the thing. Let's think. I think I'll also have to think a little bit. Okay. What can we do? So how do you bring in differences here? That is the idea. One very natural, yes. Yeah, that's certainly one way. Yeah. K plus 1 whole square. This is one of the ways. Someone might do it as k square minus 1 plus 2. That's another way. But yeah, we'll do with this. Let's we get this right. Now, once you do this, right, then there's already an idea here. That is, see, you can just, you have this. Now you can simply, you have this expression, right? Yeah. This part you can forget about because you have already done it, right? If you want to sum this grand thing, okay. So if you want to sum this whole thing, just to expand it, what it will look like is we will have 2 square times 1 factorial minus 2 times 1 times 1 factorial plus, put k equal to 2, you get 3 square times 2 factorial minus 2 times, the 2 times will always come. Okay, 2 times 2 factorial, and again 4 square times 3 factorial minus 2 times 3 into 3 factorial, and so on, right? But these things, we have already dealt with these things, right? We have already seen how to, add them up. So we can just simply forget about it. Okay. I'm not saying that's the best thing to do, but at least it seems like that, right? That we should immediately simplify things that we can simplify, though that is not always the, best thing to do. But yeah, so we will just now we will just focus on this problem. So what is next? What should we do now? So this is will look like this. As I already wrote it. I should have not removed. So this would, no, but the 2 is just multiplied by 2, right? Every term is multiplied by 2, so there's no problem. Yes, absolutely right. That's just the 2. So yeah, so that you should just write it out, you will understand. Okay. So that's right. I mean, you guys should write this solution in detail again, maybe. But yeah, in any case, the point is we have this. Yeah, this is what it is. This is what our task is now. And so on till what will now be the last term. It will be, I'll just remove this, right, the last term here. It will be 51 square times 50 factorial. Now our task is to add this. Now this is a similar problem, but Yeah, it's the same problem. That's a good thing. So I just want others to just now do it on just do this on your own. Okay, if you have already got it, it's very good. But others just think about this now. Okay, so please finish this. I'm not finishing this intentionally. Please finish this. It's very interestingly, right? It just turns out. In fact, the way I was doing it was much worse than the way it has been suggested now. Okay, I was doing it like this: k square minus one plus two k factorial, and then so on, so on. It just got very messy. In the end, I think I knew I would get the answer, so it was coming something which I would say. But this is so simpler, so much simpler. Okay, so please work this out. Okay, take the terms, work it out. So yeah, that was the second problem. Now I would like to come back to the one logic question that we had. Okay, no, we don't have time. So leave it. We'll do it the next. Okay, we will do that the next time. And for now, let us just, because that will take a bit more time. I think next time I'll just start with that. Okay. Yeah. So for now, let us just do one small problem again, which is basically a third theme. Okay, this theme goes into calculus, needs calculus later on. So this is the third kind of thing. So we saw one based number theoretic, one is a summation and algebra and manipulation and combinatorial interpretation and so on. The third is size. What is the size? Size of n factorial. This is the finally this is what we would want to understand. How much is n factorial roughly? Can we say it in terms of some simpler function? We kind of looked at a similar problem in Monday's class, similar, but for time being, we just want to do some very simple stuff. Okay, we want to show, okay, show that for any n, n factorial squared. So this is obviously but n times n factorial times n factorial is less than. We want to show this that for any n, this is true, is n to the power n times n factorial. I think this side is easier, times 2n. 2n factorial. So you go to, you multiply up till 2n. Okay. Let's see. I mean, let's just do this part first. Okay. Finally, we see that all these questions can actually be done only using combinatorics, or some versions of them can be done. Even the divisibility questions can be done through combinatorial. Some combinatorial problem will tell you that many power will divide and so on. So later on we'll see. So for example, what I'm trying to say is that we had this 60 factorial, right? And we showed that 2 to the power 30 or something was dividing it, right? We did it number theoretically, but we will also, maybe after some time, we will think of a combinatorics question whose answer will be this. And so that will prove it's an integer. It will not tell us the exact, it will not tell us the highest power value, but it will still help us to do a lot of things. Okay. So, and also these we will solve two combinatorial problems and we'll show that one clearly has a higher solution. And so that we also do. Similarly to the summation question. Okay. But those will be on the harder side. We'll see them slightly later. Let's try to show this one. Then we can end the class for today. Yes, right. So for small examples, it's pretty obvious. If you take 2 factorial times 2 factorial, it's clearly less than 2 to the power 2 times 2 factorial, right? Okay, in this case, it's in this case also is less, right? And 3 factorial times 3 factorial, it's less than 3 to the power 3 times 3 factorial. In some sense, this inequality is obvious, isn't it? Can anybody give an explanation as to why this is true? I mean, just take some. So if you don't want to think about it, and just take some number and try to reason it, right? Without the calculation, of course. Some reasoning. Right. Yes. Yeah. You see, it's absolutely right. So it is very clear if we just do this term by term comparison. Okay. And we have seen this kind of reasoning when we were doing the series thing also, right? We take the terms and we compare it with something like 2 to the power and something like that, right? So this is what is happening. You see, it's formally speaking, what we have done is something very simple. We have, okay, 1 is less than n, 1 is less than n, 2 is less than n, 3 is less. This is a rather more easy question in that sense. But yeah, if you don't get the idea of comparison, then it can catch you off guard. This is this, now just multiply them. It's clear, right? And a second n factorial, obviously, you can cancel out. Doesn't matter. Doesn't add to anything. Okay. Is this idea clear to everyone? Okay. Yeah. Let us. So let me not do this, but just maybe for homework, I'll also maybe send some more interesting questions. I think, but these are good to get started. Is this so today? The focus was to just do different variations, not go very deep into one topic, into one type theme, or just to the I was already writing it, right? What was it? 2 factorial. 1 second. Yeah, it was 2n factorial, right? And this is also very simple. I mean, similar kind of reasoning you have to use. Just think about this. Just think about this. Take your time and think about this. Then we can discuss it next time. Okay. And maybe meanwhile, you guys can also think about this. N by 2 to the power n. And just so for this, just take numbers. Just take numbers, small numbers, and do see the pattern. Then take a big number and try to give a reasoning, right? Something like that. Try to see which one is bigger, and then also try with this. Okay. Yeah. Obviously, we know that this is bigger than this, but the real challenge is n factorial bigger than this or less, or and then with this. So it's all open-ended. You have to decide. You have to take examples and see. Okay, so compare these three with each other. Take small cases and try, and then maybe go for bigger ones after that. We just try how much you can. We will discuss the techniques next class. Okay, so then that's it for today. Thank you. Maybe meanwhile, this week on Wednesday, I will start a new topic. I'll say the details for those who need to. If it's too easy for someone, I will not mention and so on. In any case, we'll decide that. Thank you.